Can you believe that just 90 minutes of solar energy reaching the Earth is equivalent to the amount of energy the entire world uses in 1 year? But what is even more remarkable is that humans can capture part of this enormous source of energy using panels with almost no moving mechanical parts. No turbines, no pistons, no fuel being burned, just sunlight striking the silicon cells beneath the glass, and electricity can be generated directly. So how does sunlight actually become electricity? And how is a solar panel manufactured to do this every day? Join Factron Process as we explore the entire journey from the factory to the moment the system begins generating power. Once an expensive technology used almost exclusively for specialized applications, solar panels can now be found everywhere, from residential rooftop tops to solar farms stretching for miles, becoming a familiar part of the modern energy system. They are made from a very familiar material, silicon, derived from silica found in sand and quartz. But before it can be used in photovoltaic cells, silicon must be refined to an extremely high level of purity, then exposed to temperatures that can reach 2000 degrees Celsius, formed into large crystalline blocks, and sliced into wafers nearly as thin as a sheet of paper. These extremely thin and fragile silicon slices are then further processed to absorb light more effectively, generate electrical current, connect into strings, and finally become sealed beneath protective glass. And from here, the journey of transforming a material that begins as sand into a solar panel capable of generating electricity for decades truly begins. The process begins when quartz sand is mined, crushed, and sorted to remove rock, soil, and other unwanted impurities. The material that meets the required specifications is then fed into an electric arc furnace together with carbon. Under extremely high temperatures, the carbon reacts with the oxygen in silicon dioxide, removing the oxygen from the material and producing raw silicon. But the material coming out of the furnace still contains many metallic impurities and cannot yet be used for solar panels. The silicon therefore undergoes several stages of deep purification before being melted again inside crystal growing equipment. From the molten silicon, the factory produces long, uniform crystal ingots, which are then shaped and ground before being sent to wire-cutting machines. Arrays of extremely fine wires continuously move through the silicon ingots, slicing them into thousands of wafers with nearly identical thicknesses. At this point, the material has the shape required for a photovoltaic cell, but the wafer itself still cannot yet convert sunlight into electrical current. For the wafer to respond effectively to light, the next stage involves changing both its surface and its internal electrical properties. One of the first challenges is that silicon can reflect more than 30% of the light that strikes its surface. To reduce this, the wafer is textured, creating countless microscopic structures that make it more difficult for light to bounce directly away and give it more opportunities to penetrate deeper into the material. Next comes doping, in which a very small amount of an element, such as phosphorus, is introduced into the silicon to change the electrical properties of the wafer. This process helps form the necessary electrical junction, allowing the charges generated when light strikes the material to move in a specific direction and create an electrical current. The surface is then coated with an extremely thin anti-reflective layer, which further reduces the amount of light lost, while also contributing to the blue or dark blue color commonly seen on photovoltaic cells. Precision at this stage is extremely important. On modern production lines, even a printing misalignment smaller than a grain of salt can affect the cell's ability to collect and conduct electricity. Depending on the cell architecture, the shape and arrangement of this metallic grid can vary. Only after this series of changes, most of which are nearly impossible to see with the naked eye, does a silicon wafer truly become a cell capable of converting sunlight into electricity. A single cell can already generate electricity, but to achieve the power required for a complete module, many cells must be connected so that they work together. On many modern production lines, finished cells are divided into smaller sections using lasers before being interconnected. One common design is the half cell, in which a cell is cut in half. Because the current flowing through each section is reduced, resistive losses and the amount of heat generated can also be reduced. Therefore, cutting cells into smaller sections is not intended to save silicon, but to improve the electrical characteristics of the entire module. On high-speed automated production lines, a stringing machine can process more than 70 cells per minute, while still maintaining their positions with accuracy down to tiny fractions of a millimeter. When the cells are connected in series, their voltages are added together, allowing dozens of small electrical sources to combine into a much larger output. Because silicon is extremely thin and brittle, even a tiny crack or a poor quality connection can affect the performance of the entire string. For this reason, cell positioning and connection quality are carefully controlled throughout the assembly process. The cells can now generate electricity together. But this structure is still far too fragile to directly face rain, dust, moisture, and decades of outdoor exposure. To protect the cell system while still allowing sunlight to pass through, the factory begins enclosing it within a multi-layer structure. At the front is usually high transmission tempered glass, designed both to withstand mechanical impact and to allow as much light as possible to reach the cells. A transparent encapsulation layer is placed on top of the glass. EVA, a transparent plastic film used to encapsulate and secure the cells, is one of the commonly used materials, although not every module is required to use the same type of material. The cell strings are aligned and placed onto this layer, then connected together to form the electrical circuit of the entire module. Another encapsulation layer is placed above them, followed by a protective rear sheet. In glass modules, a second sheet of glass may be used instead of a traditional back sheet. Before the layers are permanently sealed, the module may be inspected using electroluminescence, commonly known as an EL test. When electrical current is passed through the cells, they emit radiation that cannot be seen by the human eye, but a specialized camera can record differences between active regions. Interestingly, a cell that appears completely intact to the naked eye can still reveal microscopic cracks in an electroluminescence image. Only after the internal structure meets the required standards are the separate layers sent to the lamination stage. The layers are now in the correct positions, but to become a solar panel capable of surviving outdoors for many years, they must be bonded together into a sealed and stable structure. And this equipment is far from small. On one industrial production line, a solar panel laminator can weigh around 120 tons and stretch up to 36 meters long. Air trapped between the layers is removed, while heat gradually softens the encapsulation material, allowing it to conform tightly around the cells and bond them to the glass and rear protective layer. With commonly used encapsulation materials such as EVA, this process typically takes place at around 300 degrees Celsius for 15 to 20 minutes, although the exact parameters can vary depending on the panel design. Removing the trapped air is extremely important because even a single bubble or remaining void can become a weak point, allowing moisture to enter and reducing the durability of the panel over time. After lamination, excess material around the edges is trimmed away. An aluminum frame is then installed around the panel to increase structural rigidity and provide mounting points when the module is installed on its support system in the field. On the rear side, a junction box is attached to carry electricity from the cells into the external cables. Inside the box are usually protective components that allow current to bypass a poorly performing section, such as when part of the panel is shaded. At this point, the solar panel has reached its final physical form. But its appearance alone cannot reveal how much electricity it can actually generate, or whether tiny cracks have appeared inside during the lamination process. For this reason, before leaving the factory, the module must undergo a series of inspections to confirm both its internal condition and its actual power generating capability. Electroluminescence testing may be performed once again after lamination and assembly, because a cell that passed inspection earlier can still develop small cracks during later manufacturing stages. The module is then tested for power output using a simulated sunlight test, commonly known as a flash test. A high-intensity light source illuminates the entire surface for a very short period of time, while the system simultaneously measures current and voltage to determine the module's electrical characteristics and power output. The results are typically referenced to standard test conditions within a radiance of 1000 watts per square meter and a cell temperature of 77 degrees Fahrenheit, equivalent to 25 degrees Celsius. Therefore, a rating of 450 watts or 500 watts on the label does not mean that the panel will always produce exactly that amount of electricity outdoors. Instead, it represents the power measured under the same standardized conditions so that different products can be compared. However, producing the required amount of electricity during a short test is only part of the requirement. Representative samples may also undergo testing involving temperature, humidity, ultraviolet radiation, mechanical loads, and other environmental conditions to evaluate their ability to maintain structural integrity and performance over long periods of time. That is why a solar panel that appears so simple can be designed to continue operating outdoors for around 25 to 30 years, or even longer. Once the final tests are completed, the factory's work comes to an end, and the real-world performance of the panel will then depend on where it is installed, the direction from which it receives sunlight, and how the entire electrical system is connected. After leaving the factory, the solar panels begin an entirely different journey. Depending on where they are used, they may be installed on the roof of a house or spread across solar farms, stretching all the way to the horizon. Although the scale may differ, the objective remains the same. Secure the panels where they can receive favorable sunlight, connect them together, and deliver the electricity they generate into the system where it will be used. On rooftops, the process usually begins with an assessment of the available area, the direction of the roof, and any locations that may experience shading. Technicians then identify the load-bearing points of the roof, secure mounting brackets, and install metal rails above them. The panels are lifted onto the roof one by one, aligned, and locked onto the rails using specialized clamps. Underneath, the wiring is organized neatly, the panels are connected together, and the grounding system is completed before the generated electricity is sent to the inverter. But on massive ground-mounted solar farms or installations built across desert regions, everything takes place on an entirely different scale. The site is prepared before thousands of steel piles are driven deep into the ground. Support structures are then assembled into rows stretching for kilometers, and only after that are the panels delivered, aligned, and continuously secured into position. At some projects, entire rows of panels are mounted on solar tracking systems. One such mechanism can rotate around 90 solar panels with a total structure weighing nearly 4 tons, gradually changing its angle throughout the day to follow the position of the sun. Once installation is complete, thousands of panels are connected into strings, and the direct current begins to be collected through large cable networks. At many utility-scale solar power plants, the DC system can operate at around 1500 volts before the electricity is sent to an inverter and converted into AC. The transformer then raises the AC voltage to a medium voltage level before the electricity is sent to the substation and fed into the grid. From a few dozen panels on a residential rooftop to millions of panels spread across vast areas of land, the final principle remains the same. Only when the mounting structure, wiring, inverter, and downstream electrical system are fully connected do individual solar panels truly become a source of electricity capable of powering a home, a factory, or an entire region. Once installed and connected, solar panels can become part of many different types of energy systems. On residential rooftops, they generate electricity directly for everyday household appliances. On large factories and warehouses, thousands of modules can make use of vast roof areas to supply part of the electricity needed for industrial operations. At a much larger scale, hundreds of thousands of panels can be combined into solar power plants, stretching across miles of land. But the technology is also especially useful in remote areas far from the electrical grid, where solar panels can power water pumping systems, telecommunications stations, and other independent equipment. When combined with energy storage systems, part of the electricity generated during the day can also be stored for later use. From a small rooftop to an enormous power network, the same silicon-based technology can serve completely different energy needs. From the original grains of quartz sand, silicon has gone through purification, crystal formation, wafer slicing, photovoltaic cell manufacturing, interconnection, and lamination into complete solar panels. After a series of inspections, they are transported into the field, installed in enormous arrays, and connected to electrical systems to turn sunlight into usable electricity every day. That is the complete journey of transforming one of the most abundant materials on Earth into a technology capable of harvesting energy that comes directly from the sun. How large a role do you think solar power will play in the future of the energy industry? Share your thoughts in the comments, and don't forget to subscribe to Factron Process to continue exploring how the technologies that power our world are actually made.